Okay, it's 2025, October 4th, approximately 6:23 p.m. I'm continuing on the backup phone since previous phone ran out of storage apparently, which is weird, but I should have kept an eye on that. But anyway, we were on 4.6-2, and we were discussing, we had just said, what did we just say? Said an f is non-negative, and, well, what can I say? I'll say this, okay? So we were at the setup. Now let's move on to say then for all n greater than or equal to n naught, f of n is greater than or equal to a over c times f of n divided by b. Now, we fix n greater than or equal to n naught, and choose the largest integer t greater than or equal to 0 with n divided by b to the t greater than or equal to n naught, and iterating how do I say this? Iterating this case. We'll call this case 1. Iterating 1 times t, t times yields what? Yields f of n greater than or equal to, open parentheses, a over c, close parentheses, to the t, times f of n over b to the t. So you can sort of see that by, this is supposed to be a t here. There we go. Somewhat. Yeah, so we're iterating this t times to get this. And so what can we then say? Well, set m to equal n divided by b to the t to be within the starting closed interval and not to the open interval, to the open part, b n naught. So setting that, what do we then have with all that we've said previously? Face this. Okay, so with that in mind, we can say, so f of m is greater than or equal to f of n naught, which is equal to k to equal to k, which is greater than or equal to 0. What do I say for k? Some k greater than or equal to 0. So f of n is greater than or equal to k times a over c, times k times open parentheses a over c to the t, and this is equal to k times b to the t log base b of a over c, and this is equal to k times open parentheses n over m close parentheses to the log base b of a over c, which is in fact greater than or equal to some k prime, which we'll define here a little more succinctly, well, a little more explicitly, n log base b of a over c for k prime constant greater than or equal to 0. And this is because, m is less than b and naught is bounded above by a constant multiple of 1. Okay, so what more can we say on this? Gosh dang it. I don't like that. I don't like how it doesn't cover most of what's there. Alright, I'll just have to keep that in mind. It's, where is that? It's right under here. It's where it's closed off. Okay, so let me just make that line so that way I know where not to draw underneath. Okay. So let's continue and just say let's define epsilon to be equal to negative log base b of c, which is equal to log base b of 1 over c, and have that be greater than 0. Well, it would be greater than 0. Then what can we say with all that we've already said previously? Well, we can then say log base b of a over c is equal to log base b of a plus epsilon. And what does this show? Well, we then have, therefore, f of n is equal to big omega of n to the log base b of a plus epsilon, which is what we were looking for. And we can conclude, let me conclude with something on this exercise that we can have as a takeaway, that okay, there we go. So, whoops. So, the regularity condition, from this, we have that the regularity condition alone forces polynomial growth above n to the log base b of a by a positive margin epsilon. So, it's supposed to be an epsilon, so case 3 of the master theorem need not additionally assume f of n is equal to big omega of n to the log base b of a plus e. That follows from a regularity, as we've discussed. All right. Okay. So with that in mind, that's it for 4.6-2. Now let's move on to 4.6-3. For 4.6-3, we have, well, 0.6-3. What do we have? Well, we have for g of n is equal to the summation from j equals 0 to the floor function log base b of n of a to the j times f of n over b to the j. We want to prove that if f of n is equal to theta of n, n to the log base b of a over log of n, then g of n is equal to theta of n to the log base b of a times log of the log of n, and we want to conclude that a master recurrence t of n is equal to a times t of n over b plus f of n has solution t of n is equal to theta of n to the log base b of a log times log of a. Okay, so intuitively, how can we think about this? Well, let's let variable s equal log base b of a. Each summoned simplifies to a to the j times f of n over b to the j is roughly simplifies to, like I was saying, a to the j times open parentheses n divided by b to the j close parentheses to the s over log of n over b to the j, which is equal to n to the s over log of n minus j log of b. So g of n is n to the s times a harmonic sum over the grid log of n, then log of n minus log of b, then on and on and on, which totals to theta log of n log of n. So theta log of the log of n. So let's do this a bit more rigorously. Just erase this first. Goodness gracious, okay. I think this is where, right, no, I can go a little bit lower, right here. Yeah, that's about it, okay. So let's let s equal log base b of a. Well, then we can say each summoned. Well, no, we can't say that, not yet. We actually have to show that. And let's define the capital L here to be equal. Let's make our lives easier like we did in the previous problem to say L is equal to the floor function of log base b of n. So we don't have to say that each and every single time. Well, then there exists constants. There exists constants z less than c sub 1, which is less than or equal to c sub 2, such that c sub 1 times x to the s over log of x is less than or equal to f of x, which is less than or equal to c sub 2 times x to the power s over log x for all x greater than or equal to 2. So we have that. Similar to regularity in a way, but you know, it's more so, how do I say? well, this is more specific to this case. I guess is my best way of saying that. But, well, what can we then say? Well, then we can say that c sub 1 n to the s of the summation from j is equal to 0 to L minus 1 of 1 over log of n minus j times log base, log of b is less than or equal to g of n. And what further can we say of g of n in relation to what we already have? Well, that this is less than or equal to c sub 2 times n to the s from the same summation distance. I don't know if that's a proper term, but just summation from j is equal to 0 to L minus 1 of log n minus of 1 over log n minus j log b plus this is going to be, hate running out of space, it's so freaking annoying, big O of n to the s. Okay, and so this is where, gosh, freaking dang it, I hate running out of space. Just like anywhere, just like out of storage space, I have to like restart the video on a different device. It's so freaking annoying. Or on the board, I have to erase the entire freaking board. Gosh. Okay, and this is where we isolated, continuing from earlier, where we isolated at most one last term. J is equal to L, which contributes big O of n to the s. So let's let c equal log b greater than 0. Well, then their inner sum equals, not going to let the space sneak up on me this time. Okay, I'm going to have plenty of space. Equals the summation from j is equal to 0 to L minus 1 of 1 over log n minus jc. Oh, come on. Which is equal to 1 over c of the summation from I is equal to 1 to L of 1 over I, which is equal to 1 over c times h sub L, which is equal to theta of the natural log of L, which is equal to theta of the log of L, which is equal to theta of the log of n. That's a lot to say. And by the way, this is defined. So like h sub L, I'm saying that that's equal to this, and this roughly like, you know, colon equal, that means like it's defined is equal to, I think is my best way of putting it for now. And this is because what? Because L is equal to theta of log base b of n, and freaking hell, gosh, freaking dang it, man. I have to keep doing this erasing thing, and I have to wait on that storage, and I'm very impatient as it is right now because I'm low on time. But, and changing log bases, fudge, log bases, only affects constants. There we go. Okay. Therefore, finally, we can say g of n is equal to theta of n to the s log of n, which is equal to theta of, open parentheses, no, of n to the log base b of a times log of n. All right? So that's what we can say about that. Now, how about for, okay, conclude that the master recurrence, dealio. So let's go back to that. What can we say on master recurrence? T of n is equal to a times t of n over b plus f of n. What can we say? Does that have that solution? Well, by lemma 3, which I for some reason freaking forgot to put on here, which is ridiculous. I should have had lemma 4.3 here. That's just really annoying. Hopefully it's like contained within the implications of what we've already said. But for freak's sake, we can say of the master occurrence that by lemma, so I remember writing this down, it was right freaking in front of me back then, but for now, it's like, you know, it's in the book, and the book is freaking massive, and I'm in here, I have access to it, but I'm not going to look at it right now. I mean, if it's wrong, it's just, you know, correct me and let that be so, but by lemma 4.3, well, actually, let's go back. Yeah, okay, so just based on the previous problem, we can say this. It harkens to lemma 4.3, which is that special case of case 3, if I'm not mistaken. Case 3 does not, we're separately assume f, okay. So, by lemma 4.3, we can say that t of n is equal to a times t of n over b plus f of n solves to t of n is equal to theta of g of n. So, finally, we can say t of n is equal to theta of n to the log base b of a times log of n. Thank you so very much, you long-winded problem. All right, that is it for 4.6 exercises, and that is it for now.